Hi everyone, this video we're going to be looking at the waves quiz that I just gave you. So what I have here is just a little graph, and it's a graph that's showing a lot of information. So it does show a wave on here, and you can see here the vertical axis here is going to be amplitude. Remember, amplitude is the same as energy. The more amplitude you have, the more energy is associated with a wave, right? So this would be your energy. So the more energy, more amplitude. We also have this. We have a wavelength. The wavelength is where the motion of the wave repeats itself. So the wave, if you look over here, goes up, down, and back up. And where it repeats its motion would be right here. So from here to here would be one wavelength. I could also measure it from the top of a crest to a crest here. That's a wavelength. And it could be anywhere else, even here to here. So you can measure the wavelength in many spots, but it's always going to be the same thing. So when you're measuring the wavelength, it has to be in a distance unit. So I'm not using this scale. Be careful. I'm using the scale at the bottom here. It's going to be this one right here. So the wavelength is going to be 20 centimeters. Again, be careful that you're recording the information from the correct scale. Now for the period, it's how long it takes one complete vibration. In other words, how long does it take a wavelength? So it's going to be the same thing from here to here, but I'm looking at how long it takes, not the actual distance. So the length of time would be 4 seconds. So that would be the period of the wave. It takes 4 seconds for this wave to occur. Now, what's the frequency? Well, frequency is how often the wave occurs every second. And to get that, remember, the frequency is equal to 1 over the period. They're reciprocals of each other. We saw that earlier. So here, if I go 1 over period, 1 over 4 seconds, the frequency is 0.25 hertz. In other words, every second I've got a quarter of a vibration. Let's check to see if that's true. So again, look, here after 1 second, my wave, I only have a quarter of a wave. So this makes sense. Quarter of a vibration, 0.25 hertz is happening. All right, next one is we're looking at some wave properties. So I'm looking at something like twice the frequency. The wave is happening twice as often. So in here, we're going to have twice the number of vibrations. So we're going to have, instead of a crest, I'm going to have a crest and a trough. So just draw doubling of the wave in each unit of time. Hey, what happens if I've got twice the wavelength? That means the wave is going to be longer. It's going to be stretched out. It's going to be double the length. So here, instead of having a crest and a trough, I'm just going to have a trough. And I'm going to have part of the crest over here. So just stretching it out. So it's a longer wavelength. It's happening less frequently. So the idea is there's an inverse proportionality between the wavelength and frequency. Wavelength is longer, less frequency. More frequency, the wavelength is shorter. We looked at that earlier. Finally, phase means how much is the wave shifted. And the positive says it's being shifted to the right, and it's going to be shifted a half a wavelength. So all we do is we draw the wave a half a wavelength shifted over. Nothing fancy. And that's it. That's all you have to do for phase. All right. Now this is a different type of wave. This is what a sound wave looks like. Remember, sound waves are actually this type of wave. It's a longitudinal wave. So what's going to happen is you're going to have a series of compressions here. And these compressions, what they do is they're like maximums. And in between here, you're going to have particles spread out. These are the rarefactions. Not refractions, rarefactions. They're found in between here. Now to determine the wavelength, what you do is you measure from the center of a compression to the center of the adjacent compression. So here to here is going to be 10 centimeters. So that is the wavelength. And the wavelength is consistent. Doesn't matter where I look at it. It's going to be a 10 centimeter wavelength. So one wavelength is 10 centimeters. Okay. Now we've got an equation involving the universal wave equation. The problem is this. I only give you the frequency. What the heck? I need to figure out the wavelength. So what you're missing is the speed. And what you have here, it's a radio wave. That's why I tried to give you a hint here. Radio waves travel at the speed of sound. So 3.00 times 10 to the 8th meters per second. Speed of sound here, okay? Now, the frequency of this wave is 104.5 megahertz. What does that mean? It means 104.5 million. Remember, mega means million, or 10 to the 6th. So it's going to be 104,500,000 hertz. So to determine the wavelength, all I do is I rearrange my equation, I substitute my values, and you end up with a wavelength of 2.871 meters. It's 4 significant digits. Remember, I have 4 significant digits here. I don't include the significant digits in the speed of light. I look at the actual measurement I'm starting with over here for significant digits. Finally, I need to determine the period. Well, we know, again, the period is going to be equal to the inverse of the frequency. So all you do is you go 1 over 104,500,000 hertz, which is a really, really small amount of time, 9.569 times 10 to the negative ninth. So it's 9 billionth of a second. Very, very, very tiny quantity. And it makes sense because in 1 second, I've got 105 million vibrations happening. So one vibration doesn't take very, very long at all. And the last one, we had this, you have to look, show me the resultant wave for the interference of these two waves. When they interfere, we saw this, the waves interfere, and what happens is the amplitudes add up. So I'm just going to be adding the amplitudes for each section. So here, both of them are at 0. This higher one is going to be, where is it here? Around 0.75. This is around 0.4, so about here. And here, this one is at 0.5. This is at 1, so it's going to be positive 0.5. It should be a negative 0.5 down here. So positive 0.5 when you add up the amplitudes. And again, you just go across, and this is going to be your resultant wave. And when the waves cancel like this is an example of destructive interference. Okay, so that's about it for this part. Hopefully you've got some good feedback. Okay, I'll be looking forward to another quiz later in the week and your assessment as well. So keep going. You're doing well. Take care.